This is Brian Putt. Today I'd like to talk to you about evaluating a portfolio of oysters. Or what are oysters? Oysters are those things that have a low probability of success, but high value when they are successful. The term oysters comes from SmartOrg, who breaks up the portfolio into 4 different quadrants, depending upon the probability of success and the value of the project when successful. What often happens with these kinds of projects, these oyster projects, is they're looked at individually. And because decision makers tend to be risk averse, the projects don't get done. But is that the right way to look at them? So let's consider this portfolio of 5 opportunities. They range in probability of successes from 5 to 30. They have a cost of failure, and then they have a cost of success or development, if you will. And then there's the net present value, excluding the cost of success of the project. So think of this like the revenue. We're kind of ignoring the fiscal terms here in taxes, but that could fit in as well. So looking at the portfolio collectively, just looking at all of them, the highest chance of success for any project is 30%, but there's a 65% chance of at least one success and a 35% chance of having no successes. So over here we can see the distribution here. Here's the 35%, and here's the 65%. 65% is actually the sum of these 3 things, isn't it? So roughly a little bit less than 45% chance of having one success. And this is shown on the CDF. If we look at the whole portfolio, we can see that the individual projects are not very attractive. They have low probabilities of success, but they do have high net present value. However, if we look at them collectively, we find that the probability of success is 65%, 64%, with an NPV of $30 million and a cost of $50 million. There's only a 36% chance of having total failure. In other words, none of the projects being successful. There is a low probability of losing money. We can see here it's less than about 10% chance of losing money. But there's this long downside tail. We can look at the projects incrementally. So what I've done here is to sort the projects by DPI, Discounted Profitability Index, which I'll define as 1 plus the NPV divided by the PV discounted capital. We can see that the last project here, project 2, has a negative expected value, NPV, and this reduces the total portfolio NPV. Therefore, it's a no-brainer that we should not be doing this project. We can also look at the uncertainty in the NPV. So here's the expected value. So this blue curve corresponds to this blue curve over here. But here is the P10, and here is the P90 outcome. And as we add these different projects in DPI order, we see that the uncertainty range gets larger. So let's pare down the portfolio by project 2. What does this do for us? The NPV, given at least one success, increases to 34 from 30, and the capital is reduced to 41 from 51. The probability of success is still greater than 50. Here's this success case, more than 50. It's now 60 rather than 65, however. We did get rid of this long downside tail that we had before, and the probability of losing money is less than it was before, maybe 5% now rather than 10. So what about eliminating the next lowest DPI project, which is project 4? The chance of success is now less than 50%. You can see it down here. The NPV given success increases, though, to 37 from 34, and the capital is reduced to 32 from 41. the overall NPV curve is not changed a whole lot. This analysis doesn't give us all the answers. The decision maker still has to make a decision on which projects to include and execute. Thank you for watching this video. If you wish a copy of the Excel model, send me an email at the address brian@theputz.com. This model was built using SIPMath, but it's not necessary to view the model. If you're interested in learning more about SIPMath, you can go to www.probabilitymanagement.org, and you can download the SIPMath toolbar over here at Tools. You can download either the PC version or the Mac version.